All right, so first thing we need to do is measure the voltage of the battery. This is like my third or fourth time doing this because things just keep not working correctly. There's some weird stuff going on with the capacitors. So I'm going to connect the positive side of the battery, negative side of the battery down here. I've got it on COM and volts. And I'm going to turn this to 20 volts. All right, there we have 2.81, 2.82. I've got a sticky pad over here. We're going to put that down there to remember. Okay. Now, I've been discharging this capacitor for a while because they can have residual capacitance that just keeps, or charge that just keeps going. So now, watch what happens. You see, there we go. Watch what happens when I connect this capacitor across the battery. Ready? Watch the light bulb. Notice the light bulb is going off and the voltage is going up. As the voltage goes up, the light bulb gets dimmer. And notice that's going up. This is now, the light bulb is now too dim to see. It's completely off at this point. Okay, and notice that keeps going up. Now slower and slower and slower. Now I'm going to pause this and let you in and come back a little bit after it's charged, although I'm not sure how long I want to do that. I've got other recording to do. All right, I've waited a while now. Notice that doesn't want to go up anymore. It's staying at 2.77, 2.76. Let's read across the batteries right now. Here's the battery here and the battery here. And notice they're identical. So right now it's putting out only 2.78 volts, and the capacitor, notice I'm across the light bulb, is reading that voltage. Okay, now might it go up to 2.81 in time? Yeah, but 2.8, roughly 2.8. That can't go any higher than the batteries, and notice that this right here is off. Now, if I take the capacitor again, and I put it, no, hold on, now that it's charged, let's go ahead and disconnect it here, see what the next thing is we're supposed to do. Okay, so notice the final charge of the final voltage of the capacitor, potential difference, is the same as the batteries. Okay, that's EMF issues over there. So while the capacitor is charging, at the beginning, it's like nothing. Like it's just a path for electricity to flow. But after a while, notice the light bulb goes out as if there's more resistance in the circuit. Again, think about this as a water tank. As you're filling the water up, it's actually going in one side, out the other until inside is full. And so it fills up, but once it fills up, it stops. So it goes from being zero resistance to maximum resistance. All right, we'll try this again. It's not working perfectly today, but I think I have a little bit of idea what's going on. But, oh well. So first of all, I'm measuring current when there's no capacitor. And it's 59, 60, it's in that range. Okay, 58's not bad. All right, so now I have a discharge capacitor. I've been discharging this for a while. Let's watch what our current is through the discharge capacitor. Ready? Oh, almost identical. Once again, let's do that again. So without the capacitor, it was 59 or 58. With the capacitor, 57, 50. I'd say that's just about perfect. Okay, some of the other capacitors are getting resistance to them. I don't know why. There's all sorts of issues there. Okay, but notice it's going down the amount of current through the capacitor as it's filling up. So right after it was put in there, it was almost identical to just a wire, okay? Which again shows that the capacitor, when it's empty, is like a wire. So a discharged neutral capacitor must have what resistance? 0. So we say an uncharged capacitor is like a wire in a circuit, okay? And notice that that's going down. I'm just going to keep that going. You'll notice that now it's starting to fill up, and its resistance to the current flow is going down. Now I want you to measure across a gap. Okay, put this over here. So now we have a gap, and we're measuring voltage across the gap. And the voltage reads exactly what we did before. That's the voltage of the batteries. okay? Which we know because this is the largest resistor, so it's going to take the most voltage, which is basically everything, and there's no current flowing, so that's the voltage of the EMF, not just the terminal voltage equals the EMF because there's no current flowing. There we go. Okay, now put the capacitor, which I have discharged for a long time. Let's put that into the gap and let's see what happens. To begin with, ooh, the voltage almost went down to 0 because again, it's just a wire. So it was just allowing the current to flow right through. Sorry, you didn't see it there at the beginning. And now the voltage is going up and it wants me to wait for a while. Let's go ahead and pause it and I'll bring it back in a few seconds. Yeah, I could have done a time lapse. That would have been terribly exciting. But anyway, there you go. It's up to almost 2.7, and this sucker's been on for 10, 15 minutes. I don't know if I really want to keep it on the rest of the time, but it really will go up to eventually the voltage of the battery. I guess I'll come back. I'll leave it for another 10 minutes. We'll see where it goes. Okay, let's see how it's going. I turned this off to save batteries, and now it's up to 2.73, and that's another 10 minutes. So, I don't know. What the heck, I'll let it go for another hour or so. And there we are, it's got to be at least 30 minutes. It's almost up to the 2.81. Yeah, I don't want to do it anymore. So anyway, there's good enough. That's basically the EMF of the battery. So here that shows that this has the same voltage as that because it's a giant resistor. Okay, so when it's charging, when it's empty, it's a wire. When it's full, it's a resistor. All right, let me say that better than what I did there at the end of that video. When a capacitor is uncharged, when it's completely empty, there's no resistance to flow, so it has its maximum current, and therefore it acts like a wire, 0 resistance. But immediately it starts to charge and it gains resistance to flow, so it gains resistance as it were. It will slow down or it will decrease the current in the circuit. When it is completely full, it acts like a giant resistor or like a break in the wire because indeed at that point it cannot let more current flow. So it is like a break in the wire or an infinite resistor. These 2 points at the beginning when it's empty and at the end when it's full were called steady states. Now at the very beginning it's not steady, it's just easy. In between the transient states, this is when it has when it's increasing and decreasing its voltage, and those are complicated and the math is complicated. So to keep it easy, at the beginning, when it's uncharged, treat a capacitor as a wire. When it's completely full, treat a capacitor as a break or an open switch. Okay, we're on the back side of capacitors in steady state. We have 2 batteries, 2 equal light bulbs, and the 2 switches and a capacitor, which I have discharged for a while. So I'll just keep doing that. We want to close switch 1, and I'll have to actually put this on here. Here we go. Whoop, whoop. Okay, so here we go. So I've got the capacitor here with a switch. The capacitor can't be on yet. So here we go. The light bulbs are equally on, no problem. I throw switch 1. It bypasses the first light bulb and turns on the second light bulb because it becomes a short circuit. Yes? Well, if that capacitor's uncharged, watch what happens when I throw this at the very beginning. So at the notice that light bulb was on, this one turned off as if it was being bypassed by a wire. Oh, but now look at that one is coming on. And this one is dimming. Let's just wait a little bit and watch what happens there. Okay? So what's happening is that there's getting more voltage here, which means more voltage here, and less voltage over the second light bulb because the capacitor is charging up. So then pretty soon this is full. It actually will have the voltage of one of the light bulbs. Okay, so how did that support what we did earlier? So let me go ahead and move this out of the way and we'll take a look at the worksheet, and I want to discharge this capacitor, so let me put it like that, and so that's going to discharge. But let's take a look at the worksheet. So it says, what did you observe? So I observed that the first light bulb went off. It was bypassed. Then I closed switch 2, and what happened? It bypassed again. So how does this support what we did on the first page? It proves that uncharged capacitor is like a switch. Or sorry, it's like a switch. It's like a wire. It has zero resistance. Okay. Now let's go on to the next one. Okay, now we're on circuit 4. I have, this is red, and this is 20 to 22, and this is 10 or 11. Okay, so this is the big resistor. This is the smaller resistor. This is twice the size. So we're going to close. I'm going to use that light bulb later on. I realize it's not in the circuit. So I've been discharging this capacitor for a long time. I'm putting it over this resistor right there. The circuit is flowing there. Now I keep that on for a while. All right, so in this circuit, I've actually added an extra battery because the first time I tried this, you couldn't really see what was going on with the capacitor very well. So hopefully this time you can. I've had this capacitor discharging for a very long time. Now I'm going to charge it with the red, or sorry, the blue one first. Positive, negative. The switch is already on. Okay, 1, 2, 3. Now let's put it across it's been charging it for quite a while across the blue. Let's see if we can see anything. Turn that off just to save batteries. Here we go. Oh, it came on, but not for very long. So now let me discharge the capacitor again, connecting it to the same spot so it's discharging. Okay. That discharge for a long time. Then I'm going to put it across the red one and see what happens there. So here we go. Put it across the red and drop the switch. I'll be back in about a half a minute. Let's go ahead and attach this to the light bulb and let's see what happens. Hopefully you can see it. There, we got some light and it's going out. So we got a lot more from the red capacitor than or the red resistor than from the blue resistor. So it got more voltage across the red than it did across the blue. All right, so let's talk through what we have here. So, and put it across the light bulb, would you notice? Nothing, didn't come on. Okay, charge it by putting it across R2. Disconnect, put it across the bed. It did come on. When did it gain more charge? Sorry. When did it gain more charge? Across R2, the big resistor. Why? In series, bigger resistors have more voltage. So what happened here was when we were across R1, we only got 1/3 of the total voltage. Here we got 2/3 of the total voltage, which was enough to light the light bulb. Now charge the capacitor again with R1 and R2, but use a voltmeter to find the final voltages and record. Let's do that now. Okay, so let's go ahead and let's discharge this while I'm hooking up the voltmeter. Move this over so that you can see what we're doing here. Not sure, I don't think we need the light bulb anymore, so I'm gonna go ahead and remove that. All right, and that's gonna be where you can see it, outstanding. And I'm gonna connect it from here to here where it connects back. Okay, ready? So I'm gonna put this on, it's already working, so I don't wanna use up all my batteries. There's 20 volts. So, no voltage across the capacitor. I've got them switched, so let me throw those, or do that real fast. Okay, there you go. Notice the capacitance is going up, and after a while it's going to stop again like we did on the previous lab or previous page. I don't remember which one we were doing. Yeah, actually the previous page, right? So that's going up to 0.76, something like that, and now it's going to go real slowly. All right. So that voltage is, I'm going to write down, 0.8 something, 0.8 volts. Now watch what happens. I'm going to discharge it. Disconnect this. So I'm discharging it, and now I want to put it over the other resistor. Okay. Ready? Remember, that went up to 0.8. Well, it's past that pretty easily. Just waiting. Again, if that's double the resistance, shouldn't it be twice the voltage? So we're expecting about 1.6. And there it's starting to creep up to the top. And there's the 1.6 as we suspected. Okay, so the voltage it gains across this resistor is the maximum voltage of that resistor. The maximum voltage across the blue resistor is going to be half the maximum voltage across the red resistor. Now, if I had held it there a little bit longer, it would be exactly half. Okay, so let's go ahead and answer some questions here. Let me disconnect. Get to where we can see it, more or less. Okay, so this was about 1.6 volts. And the V across the big resistor was double, because R2 is double R1. And so its final resistance will be twice the final resistance across R1. Now, in our capacitor basics labs, we found that a capacitor stops charging when its voltage reaches the voltage of the battery. Correct this statement now that you have more information. The final voltage across a capacitor equals the total available voltage. That means it could be the voltage across the battery, or it could be the voltage across the resistor, but the maximum voltage available will be what it will charge to.